So we'll pick up from last time. So we have discussed how to find the order of reaction with respect to a certain reaction. Okay, let's do a very quick recap here on how we find. So how we find the order of reaction. Okay, remember if we have, let's say, two reactants in a reaction. Let's say A and B reacting to form products. We cannot find the order of reaction just by looking at the mole ratio in front of these chemicals. Okay, so you know when you look at a balance equation, there may be mole ratio. So those mole ratios have no direct correlation with the order of reaction. So as such, we can only find the order experimentally. Okay, so the order with respect to, with respect to, we can write it as W dot R dot T dot. And I will write it as W dot R dot T dot sometimes. With respect to each reactant, can be found experimentally. Okay, so we can only find it experimentally. We cannot find it just by looking at the mole ratio. So for example, if we are doing 4 experiments here, so just a very quick recap to remind you all what we have done in the last lesson. Okay, so if we have different concentration of A and B, okay, and then we study how the initial rate changes when we use these different concentrations of A and B, we can come to different conclusions. Okay, so let me create a set of data here for you first. Okay, for example, right. So for example, if we use 0.1 and 0.2 concentration, mole per dm concentration of A, compared to 2.00 mole per dm cube concentration of B, we see some changes in the rate. Yeah, let me also fill the other 2 blanks first, and then I'll show you some numbers. What if we have 0.2 and 0.4 mole per dm cube concentration of B, and we have, let's say, 3.00 mole per dm cube concentration of A? Do you see that every time we can do 2 experiments with the same concentration of one reactant? Yes. Well, we change the concentration of the other reactant. So take 1 and 2 as an example. We are keeping the concentration of B unchanged, right? Are you feeling hot now?
Yes. No,
I am.
Oh. So, take out your shirt. Take out your shirt.
I'll just turn it on. So you have 3.00 times 10 to the power negative 4. No. Let me show you some sample data, okay, and some conclusion you can draw from each set of data. So starting with this one, what do you see? So tell me, what do you see? When you change, so when you keep the concentration of B unchanged, so you see here these are not changed, so unchanged here, and you change the concentration of the other reactant. Let's say you double this, and you double this. Okay, so what do you see in the initial rate? If the concentration change does not result in any change in rate. Can you see that here when you double the concentration, there is no change in rate, right? Yeah. If this is what you see, the order we say is 0. Why is that? Because when you go from 4.00 times 10 to the power negative 4 to 4.0 times 10 to the power negative 4, what does that mean? It means it did not change. It means it's times 1, right? And what does times 1 mean? Times 1 means 2 to the power of 0, right? 2 to the power of 0 means 1. Okay, so you can verify that. So that means the order we say with respect to A will be 0, because no matter how we change the concentration, the rate remains unchanged. Yeah, now I want you to think about what conclusion we can draw when we observe the volume changes in the initial rate. So if I see a doubling in rate, when I double the concentration, what does it say? What is the order with respect to B then? 1. It will be 1. Because what does the number 2 mean? The number 2 means 2 to the power of 1, right? Yeah. So therefore, we say the order with respect to B is 1. So to check that you really understand what is happening, I'm making up some random data here. Okay, you tell me what conclusion you can draw from each set of data. Okay, so you can only find one set of data in the exam. Okay, any one of these 3. So let me show you another one. What about this one? You might need a calculator. So when I double the concentration of A, you don't just see a doubling in rates. Can anyone tell me what is the multiple difference between these two? You need to type this on the calculator probably. Okay. You need to tell me how many times do these two numbers differ from one another. It's not just 2 times, I tell you, but 4. Yeah, so the number 4 means 2 to the power of 2. So what can you say? What is the order with respect to A this time? Second order, okay? And likewise, okay, let me show you another set of data. Okay, what again here? It went from 3.0 times 10 to the power of 4 to this. So what is the order with respect to B this time? 0 order, because there's no change in the rate. No change in rate means it's 2 to the power of 0. So it's 0 and 2. And depending on which conclusion, okay, you have made in here, the rate equation will be different. Can anyone tell me what's the rate equation for the first set of data? It will be rate equals K, A to the power of 0, B to the power of 1. Yes, okay. And that means you can choose not to show A at all in the equation because any number raised to 0 power is 1. Okay? So you can simplify that. Okay? So you have K, B to the power of 1. So likewise, can you tell me what's the rate equation for the second set of data? A squared B to the power of 0. Okay, but I want more from all of you. Can you tell me what is the unit of rate constant for the first rate equation? So to find the unit of rate constant, what do we need to do? We need to change subject. So change K as a subject. Make K the subject. Can you do that? So make K the subject. What will you have on the other side then?
Rate divided by
B, right? Yeah, concentration of B. What's the unit of rate and what's the unit of concentration again?
Per second.
Yeah, mole per dm per second or molar per second, we say. And concentration is molar, right?
Per second.
So what's the unit?
Per second.
Just per second. Okay, so the rest of you, I want you to try the second one. Okay, so the second one. I again want you to make K the subject. This is a very common type of question. You have to master this. Okay, so make K the subject again. Yeah, why are we doing this again? That's because the unit of K is different each time, depending on how your rate equation is written. You see, sometimes it's rate equals Ka squared. Sometimes it's rate equals Kb. Well, there can be different number of concentration terms, and this will affect how you determine the unit of K. So what is K this time if I make it a subject?
Like per mole per second.
Yes. Okay, so when everything is simplified, okay, what would be the resultant unit?
Per mole per second.
Per molar per second, yes. Okay, so you have molar per second, which is the unit of rate, remember? You have molar square, which is the unit of concentration. So each concentration has a unit of molar. There are 2 of it, so molar square, right? So can you simplify this whole thing? Per molar per second. And remember, you cannot leave this as your answer. You need to put what back into molar. What does molar really mean? Mole per dm cubed. Okay, so can you do that? When you expand the -1 power back into mole per dm cubed, tell me what do you get? Remember, positive exponent term comes first. Yes, dm cubed per mole per second. Is everyone clear? Yes? Okay. So now, for the last one, I will not bother you with the rate equation because you should know how to find that out now. Okay. Oh, here's another method. Because sometimes, especially when you may not be very good at with numbers, you may want to solve this with algebra. Okay, with algebra. So here I'm going to give you another set of data.
This time.
Right. So 8.5 0.00 times 10 to the power negative 4. And in here we have, let's say 6.00 times 10 to the power negative 4. Can you use the method of algebra? To solve for the order of A and B. Yeah, of course, if you can find it by inspection, the method of inspection, you can do that. But I recommend that you use the equation. Because rate is equal to rate constant times A to the power of m, B to the power of n, which are unknown, right, at this point. These are not known, right, at this point, m and n. Yeah, so we can sub these numbers back in. So for example, for experiment 1, what can we write? So we can write 4.00 times 10 to the power negative 4 equals k times 0.100 times 2 to the power n. Like that, right? Yeah, so what I'm saying is, sometimes when they give you like some odd numbers, they are not like whole numbers, not like 2, not like 1. You can use method of algebra to solve for m and n. So, and this also explains why you need to keep one of the reactant concentration unchanged. Why do we need to do that? Because if you don't do that, you will not be able to eliminate the other unknowns, right? So you know when you have these two equations, what can you do to solve for m?
Use log.
Well, before we use log, we divide it, right? Yeah, and if you don't use the same concentration for the other reactant, remember I said this is unchanged, this is changed, right? If you also change this number, then you will have also another variable n in here, in the equation. So therefore we need to have both of these numbers to be the same, so that when I divide equation 1 by equation 2, this term will go away. Yeah, we want this n. Okay, yeah, so this is what I call the method of algebra. Okay, so you can use the method of algebra. So that's what we mentioned last time. So we'll pick up from there, okay, from last time, okay, and we'll start another part. It's the activation energy. Activation energy. So I'm sure you remember the collision theory. So remember in the rate chapter, okay, we call the collision theory. What does it say? For a reaction to happen between reactants, so for reactants to react, they must effectively collide. So they must effectively collide. So what do we mean by effective collision then? Yeah, so this is the keyword in the SE. They must effectively collide. So an effective collision must meet both of the following requirements. Do you remember the two requirements? So an effective collision must, yeah, there has to be enough speed, okay? But we don't like to use the word speed instead. We like to use enough kinetic energy, okay? So must meet both of the following requirements, which you have to memorize. The first requirement, we call it the energy requirement. So how much energy is considered enough energy? Well, it's enough energy to exceed or meet the activation energy. Okay? So write down what energy requirement means. Okay, so it means the average kinetic energy of like the reactants must meet or exceed. Well, meet or exceed can be simplified as K greater than or equal to E. So I am sure you know what inequality signs like this mean. So meet or exceed means this. Yeah, we can simplify the statements into just this relationship. So must meet or exceed, what is this? Activation energy. So I like to look at activation energy using the following analogy. Yeah, what is activation energy? Imagine you are pushing a whatever object, okay, from one side of the mountain to the other. Yeah, so first we look at the definition first of activation energy. So what's activation energy, or EA? It is the minimum amount of energy needed to kickstart a reaction. Okay, so minimum amount of energy needed to start a reaction. And below is an analogy for you to understand what is happening. Okay, why is there activation energy? So this energy is very, very useful. Imagine that you have reactant on one side of the mountain and you have product on the other side. Somehow the reactant cannot suddenly become the product because there is a small mountain between the reactant and product. So you can visualize it like this, okay? Imagine there to be like a stickman here with a football on his side, Kicking the ball to the right means converting the reactant to the product. But you know, the ball will not naturally roll to the other side, right? Because there's something blocking the way, okay? It's the mountain here. So if he kicked the ball with too little energy, so imagine that he is only able to kick the ball up to this point. Would the ball be able to roll over to the other side? No. So this is a case of Ke less than activation energy. So this is the amount of energy he provided to the ball. But yet, this is the activation energy. You can see that the arrow that represents Ke is shorter than the arrow that represents activation energy. He's not able to kick the ball to the other side. So the ball will just roll back down at him, back to the reactant side. We say this is an ineffective collision. So what happens in an ineffective collision? Things will just collide, but then they will just part ways. Okay, like this. Imagine this. You have two reactants. When they collide with too little energy, okay, what will happen to them? They will just bounce off one another. Nothing happens. Okay, this is what we mean by ineffective collision. Yeah, they did collide, but no reaction happens. Yeah, they just part ways as if there's nothing happening. So we call this ineffective collision. When the Ke is less than activation energy. However, if you provide enough energy to the football, okay, or to the reactant, so that it is able to hit this part of the mountain, so you're now providing kinetic energy meeting or exceeding that of the activation energy, well, a different story happens here. Okay, you have Ke greater than or equal to activation energy. We will have what we call an effective collision. So an effective collision will result in product formation, okay, which you can draw. So if I have these reactants colliding now, note that they are colliding with much higher kinetic energy than before. So you see the tail, it's a longer tail. So this has low Ke, and this has high enough Ke to meet the activation energy. What will happen is that they will collide and they will form products. So you see, look at this. This is a different thing than before. Yeah, so now they are joined together. So you get products. Okay? So on the left, you can write also a word equation. Reactants did not become products. Okay, there is simply no product in this case. But on the right, effective collision will mean the reactants can successfully react to form our products. Or yeah, our product. Okay, so this is your product, and these are your reactant. Is that clear? Yeah, so you see on the left, the reactants, they just part ways as if nothing happened. Okay, they come together, and then they bounce right off. Okay, no reaction. So you need to know these two inequalities. Okay, so one is Ke lower than activation energy, one is Ke meeting or exceeding the activation energy. This is important. Okay, this is what I mean by energy requirement. Okay, it's not like any particle with any energy can react. Only when you have enough Ke meeting EA or exceeding EA can you react. So is this point clear first?
Yep.
Yep, okay. So we have also the second requirement, which we call the geometry requirement. Okay, so geometry requirement. Things don't just collide with enough kinetic energy. They need to collide also with the right orientation. Okay, so reactants must also collide in the right orientation. And if we use this equation here as an example, H2 and I2 forming 2Hi. Hi, by the way, is hydrogen iodide. Yeah, so you have one H2 and one I2 forming 2Hi. So these things with two like differently sized circles, they are hydrogen iodide. So what do we mean by correct orientation? Okay, so correct orientation. They have to collide in such a way to form bonds. Okay, so for example, like this. So you have, yeah, so you have something like this happening, and then, right, so you have bond forming and bond breaking. Right, so the dotted line means the bonds are breaking. The dotted line in red means the bonds are breaking. The dotted line in green means these bonds are forming. So what happens afterwards? Okay, so you will then have these products forming. So you will then have these products forming at the end. And we say hydrogen and iodine, they successfully reacted to form hydrogen iodide. There are two molecules of hydrogen iodide. So this is a correct orientation. Okay, so you can put that maybe on the right hand side. This is a correct orientation. Yeah, so the orientation being that they are colliding in this like manner. Okay, this orientation you see that they are colliding this way and this way. What is an incorrect orientation? Okay, so this will be an incorrect orientation. Like this. So what is wrong with this orientation? So if they collide this way, well, only one HI bond can form, right? Can you see? This is an H, this is an I. When the H2 and the I2 collide this way, yes, HI bond can still form, but they can only form between this I and this H, not between this H and that I, right? So therefore, we say this is ineffective collision, okay? So we will not have a product. So incorrect geometry or orientation. So no product will result, okay? So no reaction. So this is what we mean by incorrect orientation. So only when both of these requirements are met do you have what we call effective collision. Okay, failure to meet one of these two requirements will mean a reaction cannot happen. So to understand what determines how much a reactant can react, we need to turn to what we call the Maxwell-Boltzmann distribution. Yeah, very, very strange sounding thing, okay, but draw this down first, write down the name first. Maxwell, the good news is you don't have to spell his name. These are the names of two scientists, okay, you don't have to spell their names, but make sure you recognize this. Maxwell and Boltzmann, okay, so two different scientists. They discovered something. They discovered that at the same temperature, okay, so those of you who do physics will know that the average kinetic energy increases with temperature, right?
Yeah.
Yeah, so that means a higher, what does that mean? It means a higher the temperature, the particles move faster or slower? Faster. But that's just the average kinetic energy. So they discovered that the kinetic energy of reactant particles follows a distribution. Okay, so a distribution means it doesn't have a fixed value. It has many different values with many different probabilities. Okay, so write down the meaning of the term distribution. Means the KE is not a fixed value. Instead, it has a distribution, okay, but it has many possible values with different probability. Okay, let me explain. But first, write down something that you might have learned from science a long time ago. Is average kinetic energy is proportional to Kelvin temperature. Does anyone here know what Kelvin temperature is? Yeah, we add 273 to the degree Celsius that we know, then we get Kelvin. For example, 0 degrees Celsius is 273 Kelvin. 25 degrees Celsius is 298. Yeah, we add 273 to that, okay? So this is Kelvin temperature. So can you draw this relationship on the side? So we have Kelvin temperature, and this is average KE. So this proportional relationship means that you will have a straight line passing through origin. Okay, it means the higher the temperature, so you can write down. So the higher the temperature, the higher the kinetic energy, average kinetic energy. So the higher the, so this linear straight line tells you that when you move the, when you increase the temperature from left to right, the Ke will increase from low to high, okay? So the higher the average Ke, and what does average Ke mean? It is the speed of particle. Yeah, so the faster the particles move. So the faster the particles move. Okay? But then, so what is Maxwell-Boltzmann distribution? Yeah, so then what is Maxwell-Boltzmann distribution? So if you consider like there to be a sample, yeah, imagine that I have a sample of chlorine gas, or any gas for that matter, okay? Yeah, you can have oxygen or hydrogen, any random example. Let's use oxygen as an example. So this is oxygen at 25 degrees C. And then I have some oxygen at, let's say, a high temperature, 35 degrees C. So, yeah, what will we see inside the sample? Well, first of all, oxygen is a diatomic molecule, right? That you all know, right? Yeah, so you have oxygen in here, and you have also oxygen in here. But which sample will have a higher average kinetic energy?
The right one.
The right one. Okay, yeah, so can you put down higher temperature means higher average Ke. So particles generally move faster. But these particles, they do not all move at the same speed. Okay, so let me give you an example. Maybe this moves at 100 meters per second. This is 99 meters per second. This is like 98 meters per second. They are all high in kinetic energy, but they don't all move at the same speed. Okay, so they show a spread, a distribution of energy. Similarly here, oxygen at 25 degrees, they do not all move at the same speed. So maybe some moves at 40 meters per second, 39 meters per second, some moves at 41 meters per second. They are all slower, but they don't show a single value. So we can now plot the kinetic energy as follows. So this is lower temperature and thus lower average Ke. When I plot the probability of molecule against Ke, this one you need to know how to draw. Can you label the axis? X-axis represents Ke. I have an analogy to help you understand, don't worry. The y-axis is the proportion of molecule, or you can say fraction of molecules. So fraction of molecules with that kinetic energy. So the analogy that we can use here is percent of student with that score. So you can think of the y-axis as like percent of student with that score, and that the x-axis is test score. So just like in a test, all the students will perform differently in a test. Okay, I can almost guarantee you that all the students will not score the same score at the end of the test. Some will score higher, some will score lower, and we can draw a distribution that looks like this. Yeah, so can you draw me two distribution? If I want to show what is inside this jar at a lower temperature compared to what is inside this higher temperature jar, what will we see inside? Well, for the lower temperature, like a sample of oxygen, the sample, they will travel at lower speed, right? They will travel at lower speed. So therefore the curve will look like this. Yeah, so later I want you to tell me what you notice with this curve. For the higher temperature sample, oxygen, it will have a higher temperature like this. Okay, note that when you draw these two curves, there are a few things to take note. So put down a few notes on the drawing, or you need to draw this. Okay, I'll explain the curve to you. So the drawing of Maxwell-Boltzmann distribution. So point number one is that it is asymmetric. Do you notice that it is not like a normal distribution? So you may have learned normal distribution in math, right? So what does a normal distribution mean? It is symmetric along the middle. This is not a normal distribution. It's skewed, or it's asymmetric, you can say. So let me draw this more properly. It is closer, the peak is closer to one side than the other. Okay? So it's closer to the left than it is to the right. So it is asymmetric. So that's point number one. Point number two is that the area under curve So area under curve, you can now take our highlighter. It represents the total number of molecules in a sample. Now let me ask you a simple question. If you have 10 molecules of oxygen in this container, let's just say, in the same container, 10 molecules of oxygen. When I heat it up and cool it down, does it affect the number of molecules inside? No, the number of particles stays unchanged, right? When you heat up a sample or cool down a sample. So this is exactly what is happening in here. When you take our highlighter, when you find the area under curve, so if you have learned integration in math, then you know finding the area under curve means doing integration. If we are integrating this area and we compare this area to this one, should they be different or the same?
Different.
They should be the same.
Right.
Why? Because we are just heating up the same. I know they don't look the same, right? But I can tell you that like they are actually the same area. Because the number of particles remain unchanged, right? So can you use the yellow highlighter to highlight these yellow dots in here? So if there are 3 molecules on the left, there should also be 3 molecules on the right. Because we are only changing the temperature. We are only studying the effect of changing temperature, right?
It's not, how's it that? Evaporates?
No, we are keeping it in a closed container. So nothing can escape, okay? So, and the only factor we are changing is the temperature. Okay, so when we change temperature, the number of particles shouldn't change, right? So this is why the area under curve should remain unchanged, because it represents the total number of particles. So therefore, it should remain unchanged when you change temperature. So when you change temperature. And what about the third point to note? The third point to note is that both of these curves start at origin. But both of these curves do not touch the x-axis at the end. Can you see that? Okay? Both of these curves start from origin, start from 0 meaning. But none of these 2 curves touches the x-axis at the right hand side. So this is the third and the fourth point. So can you put down the third point here and the fourth point here? So the third point is that the curve starts from origin. But does it touch the x-axis on the right? No, it doesn't. So make sure you don't let the graph touch the x-axis on the right. It touches the x-axis on the left, but not on the right. Okay? So starts from origin. And point number 4, the curve doesn't touch the x-axis on the right hand side. Now I know you might be a little bit confused right now. Okay, so this is why here I want to also show where the average kinetic energy is. So average kinetic energy at 25 degrees Celsius is here. It's somewhere to the right of this, mountain. Okay, the average kinetic energy of oxygen at 35 degrees is somewhere here. The average KE you can find it on this graph. It's somewhere on the right hand side of the P of each curve. Okay, the explanation why this is not at the highest point but to the right is complicated. It's physics. Okay, and we will not be digging into that. So just know that if you want to read the average KE from this graph, you can do it. It's somewhere to the right of the highest point. Okay, so this is the average right now, average KE at 25 degrees C. And this is the average KE at 35 degrees C. So, we can also look at the other temperatures. What will happen when we change temperature? Okay, so now on the right hand side, I wanted to draw the effect of temperature on the average KE. So write down effect of temperature on average KE. So let's pick maybe 3 different temperatures here. So I'll pick 3 different temperatures here for comparison. Let's say I have 25 degrees C, 35 degrees C, and 45 degrees C. So they might ask you to show what the Maxwell-Boltzmann distribution curve is like at these 3 temperatures. So draw what the Maxwell-Boltzmann distribution, no need to spell that word, okay, recognize it, okay, draw what the Maxwell-Boltzmann distribution curve looks like at these temperatures. And now watch what I'm doing next. Okay, so you have the y-axis. Remember the axis label. This is proportion of molecule with that Ke. And this is Ke over here. For 25 degrees, you will need to draw a curve that looks like this. For 35 degrees, the peak will be lower than at 25 and it will be further to the right. For 45 degrees, the peak will be even lower than 35, but it will be even closer to the right. So tell me what you see when you compare these three curves. Do they all have the same area?
Yes.
Yes. That means the number of particles, is it the same or different? The same. Because I'm actually dealing with the same sample. It's just that I'm heating it up to 45 or cooling it down to 25. So you can write down, this is what happens at, so you have in here, okay, maybe I should use a black color first. So this is what you see at 25 degrees, 35 degrees, and 45 degrees. So you have 45, 25, and 35 degrees. So when asked, what are the particles doing inside these different temperatures? Well, you can say, at which temperature will the particle be moving the fastest?
45.
45, yeah, 45. So you will see, wow, the oxygen particles, they are like dashing around, and that fits what you see in here. This is the average Ke at 45 degrees. It is indeed the highest, because it has the highest X value you see in here. This is the highest value. What about the same particles at 35? Well, they are moving slower, but not as slow compared to at 25, right? Do you agree? Yeah. So we have in here, you see the total slope at 25, like that. Yeah, which matches what we see on the diagram here. Where is the average Ke of 25 degrees? Here, right? Remember, the average Ke for temperature is somewhere to the right of the highest point of that curve. So you find the highest point, you move a little bit further to the right, and that's it. That's the average Ke. So you find the highest point for the 35 degree curve, you move to the right a bit. This is the average Ke at 35. Okay? And also, we notice that, so this is 25 degrees C, this is 35 degrees C, and that's 45 degrees C. So what is the effect of temperature? So write down what you see. As temperature increases, what happens to the height of the peak? Does it grow taller or shorter? It grows shorter, okay? So this is the first thing you need to know. You don't have to, actually describe this in the exam, but you have to know how to draw it. Okay, so write down the first one. As temperature increases, the height, so the height of the tallest point of each curve decreases. Okay, so the tallest point of each curve decreases, as you can see here. This is the height. You don't find it too, distracting. However, there's one thing that remains unchanged. What is it? The area under curve. Okay, so this is point number one. So write down point number two. The area under curve, however, remains unchanged. Yeah, this you must know. Okay, remains unchanged. Why? Because, again, we are just changing the temperature, right? We are just, heating up the same number of particles and cooling down the same number of particles. The number of particles doesn't change. So, which is why it makes sense that the area stays unchanged. There are 3 particles in 25 degrees, 35, and 35. Changing temperature will not change the number of particles. So the area stays constant. That's the effect of temperature. Now, any question about the MPD?
No.
No. Okay, so this is what you need to know. You need to know how to draw it. Okay. So now on the next page we look at the job of a catalyst. What exactly will a catalyst do? Okay, why is it that in the rate chapter we learned that catalysts, do they speed up or slow down reactions?
Speed up.
Yes. Okay. So effect of catalyst. Yeah, so effects of catalysts. So write down what were they? Okay. So catalysts are things that can speed up. Okay, so they speed up reaction by, you need to know how they work now. Okay, in the earlier chapter, we only say they speed up reaction without explaining why. Now we need to know why. So they speed up chemical reactions. Number one, by providing an alternative pathway. I have an analogy to show you again. Okay, so by providing an alternative pathway with a lower activation energy. Okay, this is point number one. And then there's another point that you must also know. Will catalysts be used up? No, because if they are used up, they should be called reactants instead. Okay, yeah, because that's what we call reactant. Reactants are things that are consumed. So they are not used up in a reaction. So they are not used up in a reaction because they will be regenerated. So they will be regenerated. I'm not sure if you remember the discussion on transition metals some time ago. Let me show you which equation I'm talking about. This one. I minus plus S2OA2 minus becomes I2 plus 2SO4 2 minus. This is an uncatalyzed reaction, meaning there's no catalyst added. What happens when we add a catalyst? When we add the catalyst iron 3 plus, it greatly increases the speed of reaction because I can now form intermediates. And so you have I2, and then the 2Fe2 plus will react again with our other reactant, S2OA2 minus, to form back 2Fe3 plus and 2SO4 2 minus. So this is what we mean by the catalyzed reaction. So this is the catalyzed reaction. So how many steps are there in the uncatalyzed and the catalyzed reaction? Respectively, how many steps are there in uncatalyzed reaction first? One. Yeah, because you only see one step in it. This is step one, and that's the only step. But for catalyzed reaction, there are two, because we only see two arrows here. So step one and step two. So when we draw the reaction profile, okay, so you can draw this reaction profile here. So this is just an example. So write down an example of how a catalyst works. Okay, so first I want you to draw a line that represents the reactant and product. So these are the reactants, and these are the products. Okay, maybe I'll draw it like this first. So you have I minus and S2OA2 minus. And on the other side, you have I2 and 2SO4 2 minus. This line on the left represents the reactant here. This line on the right represents the product here. Because the uncatalyzed reaction has one step, it will have one mountain. Remember, each mountain represents activation energy, right? So every reaction will have some activation energy, okay? So I'll put down an important point to note here. And what are these? These are the energy profile. So energy profile of the chemical reaction. Okay, energy profile, as the name implies, shows you how the energy changes in a reaction. So you have energy here. You can see that the reactant has a higher energy than the product. Okay, but yeah, they will tell you whether the reactant has high energy or the product has high energy. But really, the take-home message is that each reaction step will have one activation energy. So each step will have its own activation energy. So how does activation energy affect the speed of reaction? You know, some reaction can be faster, some reaction can be slower, right? So what separates a fast reaction from a slow reaction is the activation energy. So when a reaction has low activation energy, it is faster than a reaction that has a higher activation energy. So this is point number 2 that you should take note of. So point number 2. The higher the activation energy, the slower the reaction. Okay, so write this down. The higher the activation energy, the slower the reaction. So can you tell me just by looking at this mountain, is it a high mountain? Is it a tall mountain? Pretty tall, right? If you ask me. Well, but we need something to compare to. I don't. Okay, which is why now I'm going to draw you the catalyzed reaction. So can you draw another path here for the catalyzed reaction? It looks like a camel's hump. Okay, it looks like camel's hump. Why are there two mountains now? Because in the catalyzed reaction, how many steps are there? Two steps. Remember, one step, one hump. If you see just one hump, one big hump here, one step. If you see two small humps, two steps. But why are they smaller? Why are they shorter? What does that mean? Having shorter hump mean they have higher or lower activation energy? Lower. Which it means the reaction here should be faster or slower? Faster. Is that clear? You need to now relate activation energy to the speed of reaction. The higher the activation energy, the slower the reaction. Okay? So can you put down in here, the catalyzed reaction has two steps. Therefore, two humps. The uncatalyzed reaction has one step. Therefore, one hump. And that hump is taller than the two, shorter humps because it's slower. Okay? This is why we add catalyst. We add catalyst so that the reaction becomes faster, right? Yeah? So can you put this down? The uncatalyzed reaction has a huge activation energy. So this is EA, a very high EA if you ask me, without catalyst. What about the two shorter humps in here? Okay. Oh, by the way, when you label those humps, the arrow, you don't draw the height randomly. You must always draw from the left shoulder to the top of the mountain. Okay, you see there are two shoulders on the two sides of the mountain. You draw it from the left shoulder. So this is why you don't draw it like this. You don't start from the right shoulder. You start from the left shoulder. Okay, so the activation energy, you draw it from the left to the top of the mountain. Okay, so can you put down in here, these are both lower activation energy than this one. So what does it say? Now can you complete the diagram? If you have highlighter, if you have a red or blue pen or any other color you like, you can draw it. So there's something that the catalyzed and the uncatalyzed reaction share. What is it? It's the, do you know what we call this? What do we call this difference in energy here? When we compare the energy of just the reactant and product, we call it the delta H. Is isothermic, yes. So can you put down, this is the delta H. If they ask you what is the difference between the reactant and product, that's the delta H. Do you see that both the red and the green part, they have the same delta H, right? But what do they not share? Is the number of steps and also the speed of each step, right? Yeah, so can you put down the similarity between the catalyzed path and the uncatalyzed path? So this is the uncatalyzed pathway in red. This is the catalyzed pathway in green. So you can think of the catalyst as like a tunnel builder. It facilitates this stickman, okay, in kicking the ball to the right. So think about it. Without a catalyst added, how tall of a mountain must this stickman overcome before he can kick the ball to the other side? He needs to at least kick the ball to this high, right? To this tall mountain, right? But when he or she uses a catalyst is like a tunnel builder. It's like sheeting, you can say. It will create a path in the middle of the mountain. Okay, through the mountain. It's like building a tunnel through the mountain. So then, does he have to kick the ball to that height anymore? No, you only have to kick it to this height. To this height. And then the ball will roll over to the other side. So you can think of this as like a ball kicking example here. Where in a catalyzed pathway, it's easier to kick the ball to the other side, meaning the reaction is easier. But for uncatalyzed pathway, it is harder to kick the ball to the other side. Okay, so therefore the reaction is slower. Okay, so the uncatalyzed pathway is slower, but the catalyzed pathway is faster because the EA is lower. Okay, and this one is lower because the EA is higher. We should also recognize the difference between catalyst and intermediate. Do you all remember what we call things that are produced and then consumed later? And what do we call things that are consumed and then produced later? What do we call them? What do you call things that are consumed first and then produced later? Catalysts. What about things that are produced first and then consumed later? Intermediate. Yes. Okay. So can you highlight these terms? Yeah. This. If you find that they sound very similar, yes, they are. Okay. Which is why I need to summarize it for you here. Find out what iron 2 plus and 3 plus is. Can you see that in the first reaction, Fe2 plus is made, right?
Yeah.
And then in the second step it's used.
Yeah.
We call things that are first made and later used intermediate. Okay, so write this out. Fe2 plus is an intermediate because it is first made but later used again. And what about iron 3 plus? Well, we call it a catalyst. This is because what happens to a catalyst? It is first used, but later made. So remember the difference. So first used, but later made.
Because
So-
we drink that thing.
Yes. Oh, okay. Right. So now I want to discuss with you the other thing in the diagram before we wrap this up. We have the tallest part of the pathway. What do we call this point? And what do we call these points in here? So whenever you draw a an energy profile, the highest point of the energy profile we call this the activated complex. Yeah. So the highest. So write this down. So this cross, you see a cross there. So the highest point of each mountain, we call it an activated complex. Okay, so it's just like when you throw a beanbag into the air, you know there will be a highest point the beanbag can reach, right? The tallest point the beanbag can reach. So that point we call it the activated complex. So the highest point of each mountain is called an activated complex. What about a valley? Yeah, so I'm sure you all know what a valley means. Can you see something looking like a valley in here?
No.
No.
Yes.
Well, you have to use some imagination.
I'm blind.
So, no. Okay. But this one you can see a valley. Okay, like a V-shaped valley here. So every time you see a valley, we call this an intermediate. Yeah, so this intermediate actually corresponds to iron 2 plus. Okay? Yeah, so can you put a circle in here and write down the valley? So the valley of, so the valley represents intermediate. So it represents intermediate. So to check that you understand what is happening here, okay, so any question about where? No question. Any question about activated complex and intermediate first? No. So there are 3 activated complex, but only 1 intermediate in here. So now I'm going to show you a few energy profiles, randomly drawn. You tell me how many steps are there, which step is the slowest, how many intermediates, and how many activated complex are there. Okay, so put down the question first. We'll use this to summarize what we learned today. So find, number 1, the number of steps. Number 2, the slowest step. So slowest step has another name. We call that the rate determining step. So if you have a reaction with multiple steps, there's always a step that takes the most time. That step is called the rate determining step. And then I also want you to find out how many activated complexes are there. And number 4, the number of intermediates, how many are there? And number 5, well, you may be surprised to find out that you can find so many stuff from just a single graph. So the sign of the delta x. I'll do one for you as an example. Yeah, just to bring you all up to speed. Okay. So first, you can choose to copy this later, but I'll do the first one for you as an example. So I have an energy profile that looks like this, and you tell me how many steps are there. Maybe I'll tell you first. So you have this. Okay, so how many steps are there in this profile? 2 steps. Okay, so to answer the question, lazy, feeling lazy, I'll just copy this over and I'll like that. 2 steps. Why? There are how many humps? 2. Yeah, so 2 steps. If you think you will forget about like the explanation, you may want to put that down. So 2 steps because you see 2 humps. 1 hump, 1 step, 2 hump, 2 steps. That's it. Okay. Number 2. Which is the slowest step? To do this, yes. But to do this, you need to first find how great the activation energy is. Remember, you draw it from the left shoulder to the top of the mountain. This is the left shoulder, and you draw it to the top of the mountain. This is the left shoulder, you draw it to the top of the mountain. Which is longer? The left one. The bigger the EA, the faster or the slower the reaction? Slower. So which is the slower step? The first step. Yes. Okay, so first step. Right now, why? Because the EA is higher. So that's good, right? Next up, how many activated complexes are there? What are activated complexes? They are tallest point of each hump. How many tallest points are there? 2. So therefore, you can put 2. Okay, because there are 2 maximum points in here. How many valleys do you see? 1. So this is the valley. The valley. Valley means the gap between 2 mountains. Okay, there's only 1 intermediate. So last but certainly not least, what is the delta H sign of the reaction? Negative. To find delta H, we only have to find the initial and the final point and draw an arrow between them. That's it.
Okay.
From reactant to product, it's going down. So it's negative. What do we call negative delta H reaction? Exothermic. So now I will draw you 2 more, and all of you work on this together. Okay, and we'll use this to conclude what we learned today. So we have in here. Wow, okay, but that's a very interesting analogy. So. I know what you're thinking. Okay, so let me draw. Okay, that's it. Okay, I want you all to work quietly first. 30 seconds. Maybe 1 minute. You just have to find the answer to these 5 questions. Okay, so you can choose to copy that later when you get back home. But right now, I really just need you to tell me 5 different answers. Okay, for 5 answers for each of these. Work quietly. Yeah, we work quietly. Yeah, okay. We want everybody here to have a chance to work on that. So tell me how many steps are there. Tell me which step is the slowest. How many activated complexes are there? Yeah, this is the type of question you should expect. Once you do enough practice, it should be easy. Okay, so we will check the answer in 30 seconds. Draw the EA. Yeah, don't just do it in your head. Okay, I know it's difficult because you might not be able to sketch the curve right now, so you can do that.
Is it just bound between the upper part and the start and the
first one is
So it seems like most of you have got the answer. Okay, let's see. So how many steps are there in the first reaction profile? 4 steps, yes. Okay, because there are 4 humps. Excellent. And then, which step is the slowest? Second. Why? First of all, make sure you draw the EA right. Left shoulder to the top of the mountain. Yeah, you don't need a ruler for this. You can see that this is longest. So which step is the slowest? Second step is the slowest. How many activated complexes are there? 4. 4. So we have 1, 2, 3, 4. Excellent. So 4 activated complex. So how many berries do you see? 3. Yes. Okay. And they are at these positions. 1, 2, 3. Finally, what is the delta H of this reaction? Endothermic. Because when you draw an arrow pointing from the reactant, you can ignore all the humps down. Just look at the starting and the finishing line. When you draw an arrow, this points up, positive. Easy, right? Okay, so practice makes perfect. So endothermic. So finally, I think you can tell me the answer real quick as well for this one. How many?
3.
So 3. Yes, so 3 steps. And then
First step.
Yeah, the first step is the slowest, yes. And then 3 activated complex, yes. And how many?
2 berries.
2 berries. Okay, we remember to call it intermediate in exam. Okay, so 2 intermediates, 3 activated complex. Finally, exothermic, because we only look at the starting and the finishing line. Is that easy? Isn't that easy?
Yes.
Yes. Okay, so this is exothermic. So any questions so far on this? Okay, yeah. So now you understand how to interpret. Oh, maybe put down the title here first. How to interpret, how to make sense of energy profiles. So these are called energy profiles because they are drawn with energy as the y-axis. So you can see energy here. Okay, so you have energy here, energy there. So this is not to be confused with the Maxwell-Boltzmann distribution, which doesn't have energy as the y-axis. What is the y-axis of Maxwell-Boltzmann distribution again?
Proportion of
Molecule with that kinetic energy. Okay, so we'll pick up from here tomorrow. Okay, and there will be the substitute teacher will sit in. You will sit in.
Tomorrow?
Okay.
Triple lesson?
Triple lesson. Okay, will only come in the period in 8th and 9th period so far as I know. Yeah, so don't worry, just
Too much. Too much.
It's okay. Sure.
okay.
Sure.
So I will see you tomorrow. Okay? Yeah. So then I'll upload this onto YouTube like just like before. Okay. Make sure you